Hey everybody, hope you're doing great today. Let's go ahead and get started with our next unit on probability. So what we want to be thinking about this time is how do we find the probability of disjunctive statements, right? What is the probability of either getting a king or a spade? What is the probability of it either raining or it's snowing? What is the probability of me either being sick with this disease or sick with that disease, right? So how do we evaluate these probabilities? And this is something we touched on last time. This was our third axiom, but now we're going to see it in play and we're going to see the intuition surrounding it. So suppose I'm playing a card game and I'll win that card game if the next card is either a king or it's a spade, right? If I could get a king, I'll win, and if I could get a spade, I'll win. And I have this perfectly shuffled deck. So what I want to do is I want to find the probability of either getting a king or a spade. So to do this, we can think back to our just counting rule and we can wonder, well, okay, how many kings would make me happy, right? There are 4 kings out of the 52 cards. I'd also be happy if I got a spade, right? So there's also 13 spades out of 52 cards. So just based on the counting rule alone, you might initially think, oh, okay, if I have 4 kings, that would make me happy. And I also have 13 spades that would make me happy. Well, 4 plus 13 is 17. So there would be 17 total outcomes that would make me happy. That would lead to me winning the game. But as most of you are probably noticing, there's one card here that's been counted twice. There are not actually 17 outcomes that will win me the game, right? If we actually counted all the cards that will win me the game, there's only 16. So then what's the answer? Is it 4 plus 13 or is it 16? Like, how do we solve that? And the what's going on here is the fact that we counted this king of spades twice. Right? We first counted it as a card that would make us happy as a king, but it would also make us happy as a spade, but it's really only just one card. So we really, if we just counted all 4 and then we counted the 13, we would have counted that card twice. The big thing to remember about the disjunction rule is just to subtract off any double counting. Right? So that's what's going on down here. I've counted up the 13 spades. I've also counted up the 4 kings, but the thing is, one of these cards is overlapping, right? One of these spades is the same as one of these kings, so I need to subtract off that double counting. It's as if really I'm only counting 3 kings. I have all 13 spades, and then I just have the other 3 non-spade kings. Right? Or just as easily, you might think like you're just counting all of your kings and just the 12 non-king spades. But the point is, we need to make sure we're subtracting off, like if we count all of the spades and all of the kings, we need to subtract off the 1 king that we counted twice, the 1 spade of kings that we counted twice. So that's the real important thing to wrap your head around for this disjunction rule. If we want to know the probability of either phi or theta, well then that's just counting up all of the times phi would happen and all of the times theta would happen, and just make sure you subtract off any of the times you counted those twice, right? Any of the phis that were also thetas. Any of the things that while you were counting them as phis, it turns out you recounted them when you were counting them as thetas. That's what we need to make sure we're subtracting off those double counts. So that's the most important thing. Whenever we're doing one of these disjunctive probabilities, we always just want to ask, okay, is there any overlap? Just add up the 2 probabilities and subtract off any overlap. So let's compare this to another situation. Suppose I had to win if I either got a king or a jack. Well, I'm going to do the same process, right? I'm still just going to count up all my kings. Look, there's 4 of them. And I'm going to count up all my jacks. And then I'm just going to ask how much overlap is there, right? How many kings are also jacks? And, well, the idea is none of them. Right? Some spades are jacks, some spades are kings, but no jacks are kings, no kings are jacks. So it's the same formula though, right? We still say, okay, I have 4 kings, and I add to that my 4 jacks, and I subtract off the overlap. It just so happens that now the overlap is nothing. So that's what gives me my 8 out of 52. Whenever I'm saying what's the probability of A or B, I just say, okay, find first the probability of A, and then find the probability of B, and then just subtract any overlap, right? Subtract any places where you would have counted those things twice, right? Make sure we only count everything just once. So we have a particular name for when there's no overlap, right? This is something we talked about last time. When there's no overlap, we call these mutually exclusive, right? So Jack and King don't have any overlap, so we call them mutually exclusive. So really, we can just think about that as the probability of a Jack plus the probability of a King, and there's just nothing to subtract off. But the real thing to be thinking about is when they are not mutually exclusive, right? When having a King doesn't mean, right, you could have both a King and a spade. Being a spade doesn't exclude you from being a king. You could have both. And when we have that overlap, when we have the possibility of being both, that's when you want to be able to subtract off that double counting. So that's really the general idea. That's how disjunction works in probability, right? We just say, okay, what's the probability of one? Add that to the probability of the other, and then we just subtract off any overlap. So we can look at another couple of examples. If we ask, what's the probability of getting a 2 or a 3? Well, we can just look back up here and we can just ask, well, there's these 2s and these 3s, and there's no overlap. We just have 4 plus 4, done, right? So that would give me 4 out of 52 plus 4 out of 52 equals 8 out of 52, and there's simply no overlap, right? I could just put in minus 0 out of 52, right? That's the amount of 2s that are also 3s. But the point is, I'm not actually taking anything off there. So I just have my full 8 out of 52 cards. And by the way, this is a good point for me to point out. Generally speaking, I won't be reducing my fractions. And part of that is because, well, fractions are already, like, these are true to form numbers. Like, it's not like decimals are in any way more, like, real than fractions. Decimals, in fact, hide a lot of the information. But I also, just as I won't convert to decimals usually, I'm also not typically going to be reducing these fractions because seeing the fraction itself can tell you what's going on, right? If I just show you 4 out of 26, it's less intuitive what's happening here, right? It's the same number, but when you see 8 out of 52, you know, oh, that's because there's 8 cards out of 52 total cards. It's the same number, same probability, but I leave these unreduced because it can show you a bit of like the history of how we got to these numbers, and that'll be more apparent as we go. If I'm trying to find the probability of a 2 or a 3, I'm just going to add my 4 2s plus my 4 3s, subtract off the 0 amount of 2s that are also 3s, and that gives me my 8 cards that would make me happy. And then if I wanted to do something similar and I wanted to say, okay, but what's the probability of either getting a 2 or a club, right? I could do the same sort of thing. I could say, okay, well, there are my 2s. There's 4 of them. So let's go ahead and put that in first. And then I'm going to add that to the probability of getting a club. So I go in and I say, okay, how many clubs do I have? And so I go in and I grab all of my clubs. And I have 13 clubs. And then I have to ask, okay, but are these mutually exclusive? Is there anything that's both a 2 and a club? Is there anything that I counted here and there? And there is. I counted the 2 of clubs both times. So because I just want to count it once, and so far I've counted it twice, I need to subtract off one of those cards because one of those cards has been counted twice. And this is what gives me my 16 over 52. The point here is while you're evaluating the probability of a disjunction, you're just asking, okay, what are the individual probabilities and how much overlap is there? And as long as you can get those 3 things, you've got the probability of your disjunction. All right, so let's move on then to conditional probability. So a crucial thing that we're interested in probability is how does new information change how confident we should be in something, right? So if I started off thinking that, well, this team has a 90% chance of winning, and then I learned that their star player isn't playing anymore, now how likely should I think they are to win? And we're going to be looking at this again more next time too, but the idea is we need to be thinking about what we call conditional probability. So when we say that we're conditioning on an event or conditioning on evidence or information, right? It's not like conditioning in like psychology sense. These are just 2 very different meanings of the term. The idea is we're saying, okay, supposing that this information was true, what should we be thinking now? Right? If we condition on the idea, or if we assume that, if we presuppose that you already drew an ace of hearts, then how likely is it that you draw another ace next? So that's the sort of thing we want to be thinking about now. Whereas before we were thinking about brand new decks where it was just, you just have your probability space and you just ask, okay, what's the likelihood that anything happens in that space? Now we want to know, well, suppose something has happened to it in a way that's changed the space. Suppose somebody's already drawn some cards. How does that change the likelihood that you're going to get that next ace? So we can think specifically in terms of, right, what if somebody drew the ace of hearts? So we start off with this beautiful brand new deck of cards, right? All 52 outcomes are possible. But then suppose you already know an ace of hearts has been drawn. And now you want to figure out, okay, what is the probability of drawing a new ace? Or what's the probability of drawing an 8? Or what's the probability of drawing a spade, right? The point is you want to know, based on this new information, based on the fact that an ace is now gone and somebody took it out of the deck and it's not there anymore, how likely are your remaining outcomes? To do this, right, we just need to be thinking about, how does our probability space shift? So the way we represent conditional probability is with this vertical bar. So you can really just read this vertical bar as saying given or assuming. You're asking, what is the probability of theta given that phi already happened, right? So what comes after this line is like, well, assuming that we already know this stuff happened in the past, what's the probability of this new thing happening? We're supposing, we're conditioning, we're assuming that phi occurred, that you drew an ace, that you already drew your king or whatever, and we're asking, what's the probability that this next thing happens? So more technically, we define conditional probability in this way. That is, the probability that phi happens given that theta happened is simply the probability that they both happened divided by the probability that phi happened. Now, this can be not as clear as just thinking through the change of probability space, so I don't want to get too far into the weeds thinking about this. In fact, this is going to probably make more sense after we discuss our next rule. So let's think about the probability of drawing a king given that an ace has already been drawn, right? So we want to know, how likely is it that I draw a king given that somebody else, or maybe myself, right, just somebody, has already taken an ace out of the deck? How likely does that make it that the next card is a king? So we do this in 3 steps. First, we just want to clarify, what was the original probability space? So we just have our original sample space with 52 cards. And then we ask, okay, how does that change based on our new information? And that's our move here, from our brand new deck to this deck down here. And the idea is, well, instead of 52 total outcomes, we don't have 52 outcomes, we only have 51 possible outcomes. If I only have 51 cards in my deck, then there's only 51 possible things that could happen. One of those outcomes has been tossed out. I now have a new total amount of possibilities, right? So if I'm thinking back to my target over total from last time, right? Remember the idea of the counting rule was to say, whenever you want to find the probability of something, you count all of the cases where that would happen, and you divide it by the total amount of cases. So this second step in doing the conditional probability is to say, okay, you knew what your original total was, but now what does your new total look like? Your original total was 52 cards, but your new total is just 51 cards. There's one fewer card in total. We've seen that they changed the total by taking one out, but did they take out any of my target cards? No, it's taken out 0 of the kings. So I still have 4 kings remaining, but it has taken out 1 of the total cards. The probability of drawing a king, given that an ace is drawn, is just 4 kings out of 51 total cards. And something about this should be very intuitive, right? Really, all that we've done is just use the counting rule. We've simply just counted up how many kings there are, and we've just counted up how many outcomes there are. It's just that the way we counted up how many outcomes there are was we asked, okay, how many did we start with and how many did we lose? But the whole point of this is just that doing a conditional probability just comes down to understanding, how did my probability space change, right? How did things shift when I went from the original deck or the original space to my new deck, my used space, the one where things have happened, cards have been pulled out? So to be clear, the probability of drawing a king alone would be 4 out of 52, right? If I was just looking, if I didn't know that an ace was already drawn and I just thought I was staring at a brand new deck of cards, I would think there's 4 kings out of 52 cards. But as soon as I'm asking what's the probability of drawing a king given that an ace is missing, well, I know there's still 4 kings left, but now there's only 51 total cards. It's still just that counting rule, but now you can see how we get there. We just slow it down by saying, okay, what's our original space? How does that change the total? And then how does that change the target? And that's what allows us to determine, okay, based on that new information, how have things changed? How much more likely am I to get that king now that I learned an ace has already been drawn? So all of this is captured in these rules right here, right? Step number 1, what does your initial probability space look like, right? How many outcomes do you have and what are their likelihoods? And then step 2 is to ask, okay, how does that change, right? What new information and how does that change the target and total outcomes? And then finally, based on that change, okay, so what are the new results, right? How does that actually shift those targets and totals? So we can look at a handful of examples, right? So the probability of drawing a king, given that you drew a king, would be, well, you took 1 out of the total, but you also took 1 out of the target, right? So there are only 3 kings left out of 51 cards. The probability of drawing a queen, given that you drew a king, would be 4 out of 51, because there are 4 queens left out of 51 total cards. And then, right, we could ask, well, what's the probability of either getting a king or a queen, given that I already drew 1 king? And now we have 7, right? We're still doing this all in the same process, where we ask, okay, originally I had 4 and 4 kings and queens out of 52 total cards, but then I shifted that. Now I only have 51 total cards, because 1 of them is missing, and I know I only have 3 kings, because 1 of those is the one that has already been dealt, but I still have all 4 of my queens. Each one of these can be gotten by starting off with, okay, what would the probability be before I have this additional information? And then how does this information change these probabilities, right? Does it take any of the total away? Does it take any of the target away? And that's all we're doing for each one of these. A common mistake, by the way, is for these sorts of things, if I ask like probability of queen given a king, some people, like, a common mistake might be to say, oh, there's only 48 cards left because you just drew all the kings. But remember, we're not saying given drawing a king, that doesn't mean you drew all of the kings. That just means you drew 1 of the kings. You knew 1 king is missing and you're not even sure which one is missing. So that means we've lost 1 card and not 4 cards. Another important thing to mention is the difference between mutually exclusive and independent events. We've already talked a little bit about mutually exclusive events. So mutual exclusive events are ones where they can't happen at the same time. Independent events, on the other hand, can happen at the same time, because one happening for an independent event would mean nothing for the other event. So in fact, if 2 events are mutually exclusive, they're very much not independent. Being mutually exclusive means you know if one happens, you already have information about the other one. You know that one can't be happening. But the point of an independent event would be to say, hey, me knowing that this thing happens doesn't tell me anything about whether or not this other one would happen. So when we say that something is independent, what we mean is that getting this new information doesn't change our confidence in A. The likelihood that A is true, given that we know B is true, is just the same thing as the likelihood that A is true. This is what we mean by independence. Of course, this isn't true for everything. So let's look at our final rule for this week. So the conjunction rule is very similar to the conditional probability rule. And really the reason why I teach it after the conditional probability is because solving these conjunction problems typically just involves you also doing a conditional problem. So here's what I mean. Suppose you want to find out what is the probability of drawing an ace and then drawing a king given that you've drawn an ace, right? So what's the probability that you both draw an ace and then you draw a king? So, well, before we were talking about what's the probability that if I already drew an ace, right, if that was in the past, what's the probability that now I get a king, right? And we said that was 4 out of 51. But suppose I haven't done either one yet, and I want to find out what's the probability of first drawing an ace and then drawing a king. And the idea is pretty simple once we already have this conditional probability thing in place. It's just that we need to multiply them together. So, right, if I want to find out what is the probability of getting an ace first and king second, well, that's just going to be the probability of getting an ace times the probability of getting a king given that I've already gotten an ace. And right, this just comes right out of the definition of conditional probability that we just talked about, right? The probability of phi given theta is just the probability of phi and theta divided by the probability of theta, right? The probability that they both happen, factoring out the probability that that first one happens. And so the idea is if we just multiply both sides by that probability of theta, we get exactly this formula right here. That the probability of both of them happening is the probability that the first one happens, and then the second one happens given that the first one already did. That's all we're doing in conditional probability. So all that we need to do then is we just need to say, okay, so if I need to find out the probability of getting an ace and then a king, I need to say probability of an ace is, well, there's 4 out of 52 of those, times, and then I ask, okay, now that I've drawn an ace, what's the probability I get a king? And that's the thing we just solved up above, right? There's 4 kings out of 51 total cards. So that's why I say doing these conjunctive probabilities just involves you doing the conditional probability already, right here. You had to figure out based on the first thing happening, how does that affect the second thing happening? Conditional probabilities are in a sense like regular vanilla problems right after you acknowledge that you just have to change your sample space a little bit. But as soon as you change your sample space, then you use your counting rule or your disjunction rule as you always would. And the idea of a conjunction is just to do both of those, right? You just ask, what's the probability that the first one happens? And now that that's changed my space, what's the probability that the second one happens? 4 out of 52 is just the probability of getting the ace, and then 4 out of 51 is the probability of you get a king given that you've drawn an ace. And then if you want to find out, okay, so what's the probability that I do both? We just multiply them together. The idea for conditional probability is it's asking what are the chances something happens given that something else already has, right? It's taking for granted that the initial occurrence has already happened, and it ignores what the likelihood of. Right? That's what conditional probability is doing. The idea of conjunctive probability is asking, okay, but what if I don't want to ignore the likelihood that that first thing happened? What if I want to ask, how likely is the first thing going to happen? And then as a result, how likely is that second thing going to be? And that's what this conjunction probability is all about. And that's all that we're going to do when we need to solve them. We just need to first ask, what's the probability that the first one happens? And multiply that by the probability that the second thing happens given the first. So that's why this conjunction really just builds off of our conditional probability knowledge. That's why it's important that we first understand how to do those conditional probability problems. And all that those come down to is understanding how do I shift my probability space whenever something happens. So we can look at a number of examples. So the probability of getting an ace and then another ace is going to be the probability of getting an ace times the probability of getting an ace, given that you just drew an ace, right? So this will be, well, I need to draw my first ace, and then I need to multiply that times the probability of drawing a second ace. So how did my probability space change for this second card? Well, I only have 3 aces in total now, and I only have 51 cards. And so this would be the probability of getting an ace twice. What about getting a 2 and a 3? Well, I would have to get a 2 first, and then I would want to ask, okay, so now what is the probability of getting a 3 given that I've gotten a 2? And the idea is, well, okay, so probability of getting a 2, there are 4 out of 52 of those, times the probability of getting a 3 given that I've already drawn a 2. Well, there's still 4 3s, but there's only 51 total cards. And then finally, What's the probability that finally, what's the probability that I draw a club and then a spade? Well, there's the probability that I draw a club, and then times the probability that I draw a spade given that I've drawn a club, right? And so that's going to be 13 over 52 for the 13 clubs out of 52 total cards in my first pull. And then I'm going to do, right, I've drawn a club, so I'm missing one out of my total, but I still have all 13 of my spades. So I have 13 out of 52 times 13 out of 51. So just to give you a sense of the decimal expression of these, right, and which one is more likely than the rest, these are all pretty unlikely, right? The most likely thing to happen is that you get a club and a spade, right? And that will happen 6% of the time. But 1/10 of the chance of that is that you get a 2 and then a 3. And even more rare is that you get an ace and then another ace, right? Think about that. If you're drawing from a new deck, the probability that you draw 2 aces is less than 0.5%. So these are the probabilities that inform, right, how card games really work and why certain hands in certain card games are better than others. Well, because they're less likely. So that's conjunction probability. And the idea is, if you already understand conditional probability and you understood what we did on day 1 with just like regular simple probability without conditions, conjunctive probability is just multiplying them together. So the question is really then just about whether or not you're comfortable with conditional probability, and that just comes down to adjusting your probability space, right? Being able to say, well, I started with this many outcomes and this many targets, and now I have that many outcomes and that many targets. And if you're able to make that transition, then solving those conditional problems really just turns into another vanilla probability question. And those vanilla probability questions are essentially all answered with either your disjunction rule or something like the counting or complement rule, right? And in all of these, basically all that you're doing is just counting up all of the outcomes that matter for your target and making sure you don't double count anything. But really, that makes it so all of these really complicated questions about probability just boil down to these sorts of counting questions. And are you counting the right things at the right times? Okay, good luck with everything and stay safe out there.